All right, last class we left off. We had just learned about balancing chemical equations, and we stopped right before this slide. So I've already given everyone in the room a little bit of time to work on it. So if you're just getting here, we're just going to go through it. So for balancing chemical equations, the place that we want to start, especially with equations like this, is we want to look at something that's in one chemical on both sides. For this equation, that's hydrogen. Hydrogen in HCl, which is a binary acid, hydrochloric acid, and it's in H2O, dihydrogen monoxide, hydroxylic acid, whatever you want to call it, H2O, water. So we're going to balance hydrogen first, because when we balance hydrogen, it's going to change other things, and we want to get all of those big changes out of the way first. Initially, we've got one hydrogen on the left side in HCl, and we have two hydrogens in H2O on the right side. To get those balanced out, we need to add a coefficient, a number in front of HCl of 2. That doubles the amount of HCl's that we have. So now it's 2 and 2 for our hydrogens. Then we can balance everything else. So we've got oxygen that's by itself on the left side in a compound on the right side, and we've got chlorine that's in a compound on the right or on the left side and by itself on the right side. So we can balance either of those first. Let's go ahead and balance Cl because it shows up next in the left to right. It doesn't really matter which one you do. So for Cl, chlorine, we've got a coefficient of 2 in front of HCl, meaning that we've got 2 chlorines. And in Cl2 on the right side, we also have 2 chlorines. So chlorine is already balanced. And then the last thing to balance is oxygen. For oxygen, we've got 2 O's in O2. Horses need oats for clear brown eyes. That's why oxygen and chlorine are diatomic. They're O2 and Cl2. And oxygen, we've got 1 on the right side. Your inclination might be to double the amount of H2O's that we have. And that can work, but then we have to trail back, we have to circle back to other things. If we double the oxygens, that doubles our hydrogens. We would have to double our HCl's, we would have to double our chlorines, and then we would finally be balanced. So a faster way of doing that, believe it or not, is to put a coefficient of 1 over 2 in front of our oxygen, our O2. This gets us all balanced out, and then we have one more step to do. That one step is to get rid of this 1/2 that we just put there. We can do that by doubling everything. So we multiply all of the coefficients, all the numbers in front by 2. So this 2 in front turns into a 4. This 1/2 turns into a 1. This invisible 1 turns into a 2. And this other invisible 1 also turns into a 2. So we end up with 4 HCl plus O2 goes to 2 H2O plus 2 Cl2. And it's always a safe bet to go through and recheck and make sure that it's balanced. But I'm not going to do that. Any questions? Again, you can do the other way. You can not use the 1/2 and instead put a 2 in front of the H2O and then rebalance everything. You can do that. It takes a little more time. It's a little less efficient. That's why I don't do it that way. All right, moving on. There are several categories of lots of different things. One of the categories we'll be talking about is types of reactions. You've probably already taken a look at types of reactions because you had a pre-lab due for today, and we're doing reactions for that. So we're going to learn 4 basic categories of reactions. There's some other names that we can call reactions. So that's the specific types of reactions. But the four basic categories are combination, decomposition, single replacement, and double replacement. Combination is also sometimes called synthesis. So combination or synthesis reactions are where we are just combining two or more substances and we form one product. So combine two or more reactants to form one product. Usually just represented with this A plus B goes to AB. So combination or synthesis, we're just combining. Nothing crazy. An example of this is sodium metal reacting with chlorine gas. And this forms sodium chloride, which is table salt. And the equation for this is two sodiums reacting with one chlorine. The reason that we have two sodiums is because chlorine is diatomic. It's the Cl in clear brown eyes, or the coal in Brinkelhoff. And that goes on to combine to 2NaCl. So that would be a combination reaction. A decomposition reaction is the opposite. In a decomposition reaction, we've got one reactant breaking down into two or more products. So one reactant breaks down to 2 plus products. Decomposition often involves an input of energy as heat, light, or electricity. An example would be carbonic acid, which is present in any carbonated beverage. Carbonic acid is H2CO3, and it breaks down to CO2 and H2O. If you put a lot of CO2 into water, it'll naturally form a little bit of carbonic acid. If you put a lot of CO2, form a little bit more H2CO3, and then some of that CO2 can come back out. So decomposition, we're just decomposing, we're breaking down. One of our specific categories of reactions is combustion reactions. In combustion reactions, you can think of burning stuff. So like burning wood or gas, or any other fuel. Combustion reactions, we are reacting with oxygen gas, to produce heat and light. So we've got O2 as a reactant, heat and light. The heat is the more important part. Heat and light as a product. As products, sorry. So we've looked at a couple of combustion reactions. So an example here being propane fuel, C3H8 is propane, reacts with oxygen in the air to produce CO2 and H2O and heat. You will probably never see or rarely see heat written in as a reactant. You should be able to identify that it is as a product. You should be able to identify it as a product for a combustion reaction. So sometimes it's convenient for us to add heat as either a reactant or a product. For combustion reactions, it's always a product. So an example of a problem that you might see could look like this. Octane is a component of gasoline. You wouldn't be able to do all this on a multiple choice question, but write the skeletal equation for the combustion of octane, then balance the equation. So if you're given an equation like this or a problem like this, you need to know that one of the reactants is O2, and you need to know the products are CO2 and H2O. So we're given C8H18. You would need to know that O2 is a reactant, and the products of combustion, assuming everything goes perfectly, which they almost never do, are CO2 and H2O. And then we would have to balance it. The way that this type of problem might show up on an exam, I think I've given something like this before. The problem tells you that it's a combustion reaction. It tells you what the fuel source is, and then you're asked for the coefficients on them. So to balance this equation, we want to balance our carbons and our hydrogens first. A lot of our combustion reactions look the same. So to balance carbon, we need a coefficient of 8 in front of CO2 so that we get up from 1 to 8 for our carbons. For our hydrogens, we've got 18 on the reactant side, the left side. And we've got 2 on the product side in H2O. To turn that 2 into an 18, we need to multiply by 9. So I'll have a coefficient of 9 in front of our water. And then our third and final thing to balance is our oxygen. We've got 2 oxygens on the reactant side in our O2. We've got 8 times 2 for 16, plus 9 on the product side for a whopping total of 25 oxygens on the product side. So using the fraction method to balance this, since it's a little faster, we would take 25 over 2 and make that our coefficient for O2. Or you could do 12.5, 12.5. And then we come in and double everything. Boop. Big double. And thanks to technology, can copy and paste it. So we add a 2. This 25 over 2, when we multiply by 2, turns into 25. 8 turns into 16. And 9 turns into 18. And that would be the balanced combustion reaction. So again, the key components for combustion, we're reacting with oxygen gas, O2. We're producing CO2 and H2O. This doesn't include all combustion reactions, but the ones that you'll see on exams. CO2 and H2O will be products. And heat. And you should be able to balance them. Questions so far about combination, decomposition, combustion? Cool. The other 2 generic types of equations, one of them is a single replacement reaction. In a single replacement reaction, we're replacing, surprise, surprise, one thing. So one way that we might represent this is A plus BC goes to AC plus B. So A and B have traded C here. So on the reactant side, B has C. On the product side, A has C. We've just swapped one of the chemicals out. Replace one element in a compound. An example of this would be the way that metals react with acids. So for example, zinc metal can react with hydrochloric acid to produce zinc chloride and H2, hydrogen gas. So that's single replacement reactions. You've just got one chemical swapping. In double replacement reactions, We've seen these before. These were the other type of balancing equation. In double replacement reactions, we've got positive and negative ions, and they can swap to form new ions. So B and D, in this example, swap places. So instead of AB, we've got AD. Instead of CD, we've got BC. That should probably be CB, but whatever. So the idea here being that A and C would be cations, B and D would be anions, negatively charged. And then we swap the positive and the negative. We pair them up a different way. A precipitation reaction is a specific type of double replacement reaction. So two aqueous solutions, two dissolved solutions, mix and form a precipitate. Dissolved in water, form a precipitate, which is a solid. I think we'll be seeing a precipitation reaction in our lab today. And in the one where we were mixing up the little test tubes of stuff, in one of those, at least one of those, there was a precipitation reaction that occurred. All right, if we want to predict single and double replacement reaction products, we need to be able to identify what kind of ions things are going to form when we have ionic compounds. So for example, FeCl2 and Ca reacting, this would be a single replacement reaction because we've got an element that's by itself. So we need to look at the calcium and figure out whether it's more like the Fe, the iron, or the Cl, the chlorine. So what kind of element is calcium? Or what ion will it form? It's an alkaline earth metal, so it's a metal. And it's going to form what charge? 2. So Ca2+, it's a metal. Which of these two, Fe or Cl, is a metal? Yeah, Fe is the metal. And we could also figure out what charge it's going to form, but that doesn't actually matter for this problem. So Fe, iron, being a metal, these two are going to swap places. So that's going to be the single replacement in our single replacement reaction. So Fe is going to be by itself. Anytime that something's by itself and it's written out in the type of equation that we know how to do, it needs to be neutral, so it'll just be Fe. And then the calcium and the chlorines get matched up together. In this particular problem, it works out that it's balanced already because calcium's a 2 positive ion, and in FeCl2, iron is iron 2 ion. For this lower example, we want to pick which of these two, Mg or Br, is most like F. So fluorine is most like which of these two, magnesium or bromine? Fluorine is a nonmetal, it's a halogen. It'll form F-. Which of these two, Mg or Br, is a nonmetal and going to form a negative charged ion? Br, bromine. I wrote no metal, but it's nonmetal. So Br is nonmetal, and so these two are going to swap places. And since they're both halogens, we are again going to get MgF2, so it'll be the same number of halogens, and then Br2 will be by itself. Questions? They won't always necessarily work out to be this nice and neat, but these are example problems, so it's nice to have nice and neat. All right, double replacement reactions are a little bit more involved. We're doing an ion swap. So in order to predict the products, in order to predict what we write down on the right side of the equation, we want to separate our ionic compounds into cation, positively charged, and anion, negatively charged. Then swap the anions, the negatively charged ions. So we'll make them switch places, and then we'll combine them back together. So this is a little bit more involved, but the steps are going to be the same every single time. Or just about the same every single time. So the idea is, if we're just looking at this left side, we've got barium chloride and lithium sulfate. When these have the AQ behind them, that means that they're dissolved in solution, so the ions are separated out. And what we're doing with the product side is we're thinking, okay, what's a new way that we can combine these ions? We've got two positively charged ions, we've got two negatively charged ions. We could recombine them to form BaCl2 and Li2SO4 again, but that would just be our reactants and then nothing's happened. So we're swapping the anions, we're swapping the one that comes second, so that we get a new pairing. Strictly speaking, you don't have to swap the anions, you could swap the cations instead, it doesn't matter. All that matters is that you swap one of them and not both of them, because then they've just switched places and that doesn't do anything. So we are swapping to see what new ion pairs can form. So an example of this, we want to write a balanced reaction for the reaction that occurs when barium nitrate and potassium hydroxide are mixed. So barium nitrate and potassium hydroxide are our reactants. So our first step is we need to figure out what our reactants are. We need to figure out what their chemical formulas are. So using our nomenclature knowledge, barium nitrate, barium is Ba. It's an alkaline earth metal. It's going to form a 2 positive charge when it's an ion. Nitrate, the ATE ending, signals to us that this is an oxyanion. So we would go check our oxyanion sheet and we would find nitrate is NO3 minus. And then we can crisscross the charges. So this 2 will come down and become the subscript for this entire NO3 group. So we would combine this to Ba, open parentheses, NO3, close parentheses, 2. And then our other reactant, potassium hydroxide, potassium is K. it's going to form a 1 positive charge. It's an alkali metal. Hydroxide is a polyatomic ion made up of hydrogen and oxygen. So that's going to form OH minus. And these will combine in a 1-to-1 ratio. The positive and the negative charges combine. So this is just KOH. So our reactants, BaNO3 NO3 plus KOH will go on to produce something. We already have the ions written out, so we're just going to copy those and write them down below. So splitting these BaNO3 and the KOH into 2 parts. Sometimes we'll start with the chemical formulas instead of the names, so you won't have to do the nomenclature part, in which case this is a little bit more useful. Okay, so rewriting the way that these split up. And this is so that we can swap. So we're going to swap our anions and rewrite them on the right side. You don't necessarily have to follow these exact steps. This is just how I do it. So we've got barium, which is a 2 positive ion, and it's now going to be paired up with the hydroxide. So the OH minus. And we're going to recombine these. So we have to crisscross this 2 positive charge to become the subscript of the OH. So we'll have BaOH2. And then we've got our other set of ions, the K plus and the NO3 minus. Since these are a 1 positive charge and a 1 negative charge, these will combine 1-to-1. So this is KNO3. Questions? And then the last part is that we have to balance it. And our trick for balancing double replacement reactions, this typically makes things work out well. We just look for something that's not balanced on the left side and the right side. NO3 works for us in this case. So if we look at our NO3, let's do this in purple. If we look at NO3, we've got 2 on the left side, 1 on the right side. 2 on the left, 1 on the right. To get those to balance out, we would want to add a coefficient of 2 in front of our KNO3 on the product side. When we add this 2 in, it balances our NO3, but it also changes our K. So we have 2 potassiums. Let's balance that next. So potassiums, we've got 2 on the right side. We only have 1 on the left side in this KOH. So we are going to, once again, add a coefficient of 2. So we put a 2 in front of our KOH. And when we changed our potassiums, we also changed our hydroxides. So we're going to look at hydroxide next. So for our OH, we've got 2 on the left side because of that new coefficient of 2 we added. And we've got 2 on the right side in barium hydroxide. So that's already balanced. This usually means that we're done for simpler double replacement reactions at least. And then the last thing that we haven't looked at yet is barium. So we just look, and we've got 1 barium on the left, 1 barium on the right. So barium is already balanced, so we are done. If you are doing something like this, you're predicting a double replacement reaction, and you end up with a situation where you just can't get them to balance out, that means that you did the double replacement part wrong. that does happen occasionally. Normally it would be like if you forgot one of our Brinkelhoff or H7 or Horse's Knee Oats for clear brown eyes. Usually it's one of those that would trip you up. But if you recombine these in the wrong way, then that could also cause things to go a little bit weird. All right, another one that we can try that I'll give you some time to work on. This is our last slide for this chapter. Predict what will happen if rubidium hydroxide and cobalt-2 chloride are mixed. Okay, so the first thing we want to do for this problem is we need to know what our reactants are, so we need to access our nomenclature knowledge. Rubidium is Rb, hydroxide is OH, rubidium being a metal, hydroxide being a polyatomic anion. This is going to be an ionic compound. It's Rb plus because rubidium is an alkali metal, hydroxide is an OH minus. Cobalt-2 chloride is also ionic, and this 2 lets us know that we've got a 2 positive charge. So this is CO, big C, little O2 plus, and chloride, the IDE ending, letting us know that it's just Cl, the chlorine ion, which is going to be Cl minus, the chloride ion. And we combine these, in the case of rubidium hydroxide, in a 1-to-1 ratio, so RbOH. And our other reactant, we crisscross the CO2 plus and the Cl minus, and we get CoCl2. And since we already have the ions written out, we'll write down what these break into below. And then we want to swap our anions, our negatively charged ions. And I'm going to rewrite those on the right side here. So Rb plus is now paired with Cl minus. And our other pairing is CO2 plus and OH minus, hydroxide. So for rubidium and chloride, these will combine in a 1-to-1 ratio. So RbCl. And for the cobalt, it's a 2 positive charge. The hydroxide is a 1 negative charge. We can crisscross them to find out that we are going to have 1 cobalt and 2 hydroxides. And then for balancing them, we take a look at any of the elements or ion groups that's not balanced. So RbOH, the OH is not balanced. We've got 1 hydroxide on the reactant side, 2 hydroxides on the product side. So 1 and 2, and we will need to add a coefficient of 2 in front of the rubidium hydroxide to make sure that our hydroxides are balanced out. When we change that coefficient of 2, it's not just the hydroxide that changes, the rubidium also changes. So we'll balance that one next. For rubidium, we've got 2 on the left side, and we've only got 1 on the right side, the product side. So we need to add a coefficient of 2 in front of RbCl, and that'll get our rubidiums balanced. When we do that, the chloride also changes. So we've got 2 Cls. So for Cl, we've got 2 on the product side. And we've actually got 2 on the reactant side, so that's already balanced. The last thing to check is cobalt. We've got 1 cobalt on the reactant side, 1 cobalt on the product side. So we are all balanced up. Questions? Great, that's all for chapter 5.